If you're ready to do math today and you have your coffee ready, join me in the simultaneous sip. The question we're working on today is, sketch the graph of f of x equals x squared plus 1 over x plus 1. Smash that like button and let's get started. So we want to graph the function x squared plus 1 over x plus 1. The first thing we have to do is find the domain. The domain, well, we have a rational function, so we just make sure we don't divide by 0. Next, we'll find the x-intercept. So that's when our function is equal to 0. But since we have a rational function, that means our numerator is 0. But x squared plus 1 never equals 0. So there's no x-intercepts. The y-intercept is we plug in 0 for x and solve. So we get our y-intercept is the point 0, 1. Next, we want to check for symmetry. We don't have a trig function, so we know it's not periodic. So we'll check if our function is even or odd by evaluating f of negative x and simplifying. And we see that we don't get f of x or negative f of x, so our function has no symmetries. Next is the asymptotes. So we'll start with the vertical asymptotes. We'll have one at x equals negative 1. And we'll check which way our function is going to go at that asymptote by taking the limit as x goes to negative 1 from both the left and the right. When we take the limit from the left, we get negative infinity. And when we take the limit from the right, we get a positive over a positive, which will go to positive infinity. Since the degree of our numerator is greater than the degree of our denominator, there's no horizontal asymptote, but there is a slant asymptote because the degree is 1 more than the degree of the denominator. The degree of the numerator is, that is. So we do long division. And we get y equals x minus 1 as our slant asymptote. Next, we need to figure out when our function is increasing or decreasing. So we take the derivative, and we have a quotient, so we're going to do the quotient rule. And then we'll simplify. We want to find when our derivative is 0 or undefined. Those are the critical numbers. So when it's 0, that means the numerator is 0. Here we could use the quadratic formula to find that our derivative is 0 when x equals negative 1 plus or minus the square root of 2. And our derivative is undefined when the denominator is 0, which happens when x plus 1 squared equals 0 or x equals negative 1. So now we'll take a number line and we'll break it up at each of the critical numbers. And we'll take a test value in each segment of the number line. And we'll check if our derivative is positive or negative at each of those test values. We don't care what the value is, we just want to see is it positive or negative. So when we do this, we see the first segment of our number line is positive, so our function is increasing on that segment. The next segment is negative, so we're decreasing there. The next segment is also negative, so we're decreasing there. And our final segment is positive, so we're increasing. And so now we can have a quick sketch of what our curve will look like. We have a local max when our function goes from increasing to decreasing. So we have a local max at x equals negative 1 minus the square root of 2, and we have a local min at negative x equals negative 1 plus the square root of 2. And these points we could plug into our original function. When x equals negative 1 minus the square root of 2, the y value is negative 4.828. And for the other point, the y value is 0.828. To find the concavity, we need the second derivative, which again we'll get by using the quotient rule. And again, we'll have to simplify it. And here we could see we could factor out an x plus 1 from the numerator and cancel one of them out in the denominator. But just as before, we're going to take our second derivative and find when it's 0 and find when it doesn't exist. And we'll do the same thing of finding a test value and checking the concavity using those test values. So our second derivative is 4 over x plus 1 to the third. So the second derivative is 0 when the numerator equals 0, but that obviously never happens. And the second derivative is undefined when the denominator is equal to 0, which is when x equals -1. So we'll take our number line and break it up at x equals -1, choose a test value from the left and the right here, and plug it into our second derivative. When we do that, we see that we have concave down to the left of -1 and concave up to the right of -1. So what we'll do now is we'll take our number line again and break it up at every point we've broken up our number line along the way. And we'll check for increasing and decreasing or concave up and concave down on each of these segments. And it will just give us a little sketch of what our curve will look like. And once we do that for all the segments, we're ready to graph our curve. So here I draw the XY axis, draw in our asymptotes. Remember to draw in the slant asymptote as well. And we could draw our curve. And I graphed it on Desmos so we could see what it actually looks like. And make sure to label your points, your local max and local mins. Make sure to subscribe for more Coffee and Math with Dr. Weselcouch. Don't text and drive. Bye-bye.